attention to people watching this video. Run while you still can.
Alright. Write this question down. Why do we even need logarithms? Are they just here to annoy you?
Yes. Duck size and warn you.
Let's go into that. All right, write a couple of these down. And this is just basic understanding that you should have before getting into the world of logarithms. If I asked you to solve a few simple equations, let's not take too much time on this because these are simple. If I asked you to solve this equation, 2x equals 8, you could all solve it in your head probably. X equals 4. But the way that you would do this mathematically is you'd say, well, 2 is timesing x. What's the opposite of timesing? Dividing by it. Okay, so x is equal to 4. If I asked you to solve this equation, x squared is equal to 9. You could also probably solve that in your head, but the mathematical way is to say, well, x is being squared. What's the opposite of squaring? Square root. So x is equal to? There we go, plus or minus 3. So you could all solve that one pretty easy. Okay, what I'm getting at here is every mathematical operation has an inverse that undoes that operation, correct? If you add something to undo it, you subtract. If you multiply something to undo it, you divide. If you square something, you can square root. Go ahead.
Are we recording?
Yeah. So then the problem is, what if I asked you to solve this equation? 2 to the x, excuse me, 2 to the x equals 5. How would you solve this? Is there some kind of an x root you can do?
Yes.
No. There's no such thing as an x root. What is it we're trying to cancel? We're not even trying to cancel the variable. Here we were trying to cancel the variable, so we used a root. Roots cancel variables. What are we trying to cancel here? We're trying to get rid of a base. What gets rid of bases? Logarithms. Okay? All a logarithm is a function, just like a square root is a function, or multiplying something is a function. Logarithm is a function that undoes another function. Okay? This is an exponential function. A logarithm undoes that. That's why we need to have logarithms. We wouldn't be able to solve this without. Now we could estimate. You guys could all get pretty dang close, actually. Approximately what power of 2 is going to equal 5?
2.5.
We know it's a little bit larger than 2. Why do we know it's a little bit larger than 2? Because 2 squared is 4. But we know it's not larger than 3 because 2 cubed is 8. Now, is it closer to 2 or is it closer to 3? It's going to be close. So we could estimate, say, well, maybe this is about 2.1 or maybe 2.05. So we can get pretty dang close. But to get it exactly, we have to use logarithm. Okay? So let's talk about the definition.
So what kind of situation would this actually pop up in day-to-day life?
A lot, actually.
Yeah, they do it in population growth.
Population growth. You guys heard of the pH scale in chemistry? That uses logarithms. Have you heard of the Richter scale? That uses logarithms. Do you know how sound is measured?
Decibels?
In decibels, that's a logarithmic scale. Logarithms are more commonly used than you would think. They are, I would say, one of the more commonly used functions in mathematics. Logarithms are pretty useful. So, definition of logarithms. Okay. So here's an exponential function. A to the x is equal to y. If you wanted to get x all by itself, you would have to get rid of the base. You don't use roots and radicals to get rid of bases. You use logarithms. Now, and this is probably something that you remember from last year, but in case you don't, logarithms, like radicals, have different bases. For example, this problem that we did right here, what if it wasn't x squared? What if it was x cubed equals 8? You wouldn't do a square root anymore, you would do cube root. Radicals have different indices, is what they're called. Logarithms have different bases. So to get rid of a base of a, you would use a logarithm, and that logarithm has to have a base of a. Okay? And you have to do the same thing on both sides. This one would have to be a logarithm base a of y. So the definition of a logarithm is if you have some exponential function like this, it's the same thing as the log base a of y is equal to x. Notice for the similarities. This equation that I'm circling on the left, what's its base? Okay, now the one on the right that I'm circling, what's its base? They have the same base. Okay? So the first part of your homework starts off like this, really easy. Example 1, it asks you to rewrite. Really, it's just practicing going from one form to the other. If you're given something in exponential form, they expect you to rewrite it in logarithmic form. What that is similar to, you guys, we actually haven't done it this year. I think you did this last year in Algebra 2. Tell me if this looks familiar. If I gave you something like the cube root of x squared, do you remember from last year you could rewrite that in a different form using rational exponents? X to the 2/3. What we're doing now is similar to this. These two things mean the exact same thing. They're just written differently. So in example 1, if I gave you log base 2 of 8 is equal to 3. If I gave you the log base 2 of 8 is equal to 3 and asked you to rewrite that in exponential form, some students just try to remember, well, this goes here, that goes there, and they try to remember where things get rearranged. And that's fine if you want to do it that way, but it just depends on how good you can remember things. What I would recommend is to really understand what's happening here. If a logarithm gets rid of a base, then vice versa. Listen carefully to this question. If a logarithm gets rid of a base, what the heck gets rid of a logarithm? A base. You listening? So if this has a logarithm with a base of 2, what gets rid of it? A base of 2. So if I put a base of 2 down here and a base of 2 down here, then if you have a base of 2 and you're raising that to a logarithm with a base of 2, those cancel out. What are you left with? 2 to the 3rd equals 8. So rather than trying to memorize, well, this goes here and that pops up as an exponent and that, I mean, a lot of teachers like to teach it that way. You should really understand how we go from here to here. How do you get rid of a logarithm? You use a base. How do you get rid of a base? Use a logarithm. Okay? Let's try another one. Part B. If I gave you log base 4 of 16 is equal to 2. Then to rewrite that in exponential form, you would consider, okay, what type of logarithm do I have? I have a logarithm with a base of 4. What gets rid of it? So use a base of 4 right here, use a base of 4 right here. That's going to cancel that logarithm. You're left with the expression 4 squared equals 16. And you should always check that what you end up with makes sense. Does 4 squared equal 16? Yes. Does 2 cubed equal 8? Yeah. Okay, now going the other way, if we start in exponential form already, if we had something like 9 to the 1/2 equals 3, how would you rewrite that in not in exponential, how would you rewrite that in logarithmic form? Well, rather than trying to memorize, well, let's see, this moves down, that moves up as an exponent, this, you got to understand really what's happening here. What gets rid of a base? This is the base that I'm circling, right? So we would have to use a log base 9 here and also a log base 9 there. So now those cancel out. Now what you have to understand, everybody look up at the screen for a second. Initially, wasn't this guy that I'm pointing at an exponent? But if the base is gone, is this an exponent any longer? No, this is no longer an exponent. So what you're left with is 1/2 equals what? Log base 9 of 3. Okay? That's how we're rewriting from one form to another. One more just for the sake of practice. Let's do some negative numbers. 4 to the negative 3 equals 1/64. How would you rewrite that in logarithmic form? That buzzing sound is really getting annoying.
You just kind of got less.
Anyway. What are we thinking? So if we use a log base 4 here and a log base 4, those cancel. So what you're left with is negative 3 equals log base 4 of 1/64. Any questions on that? That's the first section of your homework, is just rewriting from one form to another. You good?
Yeah.
Okay. The next section is titled Basic Properties. Basic properties of logarithms. There are 17 basic properties of logarithms that we need to write down and remember. I'm kidding, there are 4. You guys didn't complain too much, like, all right, let's go, 17, yeah. Didn't quite compute, huh?
Finally.
All right, first property, the logarithm with any base, because these properties apply to any logarithm with any base. So I'm just going to use a base of b to keep it generic. Log base b of 1. Anytime you take the logarithm of 1, regardless of the base, this could be log base 2 of 1, log base 10 of 1, any base, it always equals the same thing. It does equal 0. How, was that you, Jake? How do you know? Did you just remember that, or how do you know it equals 0?
Because give anything to get a number to equal 1, those two things are 0.
That's a good explanation. Did you guys hear that? In order for any base to result in a 1, you have to have an exponent of 0. Okay? And an easier way to think about this, if you were to rearrange this in exponential form, regardless of the base, if you raise it to the 0 power, what are you always going to get? 1. So the logarithm of any base of 1 is equal to 0. Okay, good. Second property. If you take the logarithm of any base of that same number b, so the log base b of b, that does equal 1. Why is that? Well, if you start with a base of b, what power do you have to raise that to in order to get itself? 1. Okay? Yeah.
Wasn't the first property b1 and b equals 1?
Say that one more time.
So if it was log base 1 of 1, would it equal 1?
Log base 1 of 1. The base, I should have defined that earlier, the base of a logarithm has to be something other than 1. Because the base of a logarithm is analogous to the base of an exponential function, right? And if you think about last time, the base of your exponential functions had to be either greater than 1 or something between 0 and 1, but it couldn't actually be 1. Because what if the base was 1? It'd be 1 forever. So it'd actually be a constant function of 1. So that's actually a good point. The base of a logarithm can be smaller than 1, greater than 0. It could be larger than 1, but it can't be 1. We'll write this down as one of the basic properties here later on. Where were we? Oh, did we get this one okay?
Yeah.
Okay, moving on. Property 3, logarithm with a base of b of b raised to some power n. Yeah, what does a logarithm do? It cancels a base. If they have the same base, you're left with the exponent, so this equals n. Property 4. I've already kind of mentioned this, but if you start with just a plain old base, no logarithm, but just a base, and the exponent of that base is a logarithm of base b of x. Now you have to be careful on how you write this. I've seen students write it this way and then they get so confused. I've seen students say, okay, if we have b times a log base b of x, are these the same thing? No. This is how the property applies. This is not how the property applies. Because this is not a base, this is just a multiplier in front of a logarithm. So you got to be careful on how you write it. You got to make sure the logarithm is an exponent. Well, if you have a base of b and an exponent that's a logarithm base of b, those cancel out, so what would you be left with? X. Okay. Let's write down a few other things. Let's write down the thing we just mentioned. Base of a logarithm. Ooh, I'm spelling this wrong. Logarithm is either between 0 and 1, greater than 1, something else that we need to talk about, and we should talk about this way more often than we do, but domain. We don't really talk about domain very often. I don't even remember if we talked about it last time. The domain of an exponential function. Did we talk about it?
Yeah.
Okay. What was the domain of an exponential function? Always all real numbers. We really think here. Domain of, let's just choose a generic logarithm function here. Let's do y equals log. Let's do log base 2. Log base 2 of x, just some random function we're choosing here. What is the definition of domain? Not as it pertains just to logarithms, but of any function. What's the definition of domain? The possible inputs. What are the possible inputs that can go in place of x? Now, could we place anything we wanted in place of x? Let's assume for the moment that we can. Okay? And let's say, well, if x can be anything, then certainly x can be negative 4, right? If x can be anything, then why can't x be negative 4? Well, the problem with this, you guys need to watch very carefully and listen very carefully. The problem with this, if you do allow x to equal negative 4, if you were to rewrite this in exponential form, it would look like this. 2 to the power of y equals negative 4. And therein lies a big problem. Does anybody... Yeah. Say that again for those that didn't recognize the problem. This is a problem. This is an impossible situation.
You can't get a negative number out of 2 raised to a power.
Yeah, you can't raise 2 to some power and get a negative 4. Okay, I know it looks tempting. A lot of students will say, well, yeah, that can work. There's no problem there. There's a big problem here. No matter what you let y equal, you're never going to get a negative 4. And then I got a lot of students that would argue, well, no, y could equal negative 2. Okay, well, what if y equals negative 2? Does that equal negative 4? No. It equals 1/4. Is there any power of y that's ever going to give you a negative 4? The answer is no. So x can't equal negative 4. Well, maybe there's just a problem with negative 4. Maybe x can't equal negative 4. Could it equal negative 5? Could it equal negative 10? Could it equal any negative number? Could it even equal 0? Is there some power of y that you could raise 2 and get it equal to 0? That's also impossible. And then students will argue, no, y could be 0. Well, what if y is 0? You get 1. So what I'm trying to get you to think of is, what is the domain of a logarithm function? What can x be? What can x not be? Domain is parentheses 0 to infinity. Why a parenthesis and not a bracket? You can't have it equal 0. It can approach 0, but it can't equal 0. So this is similar to a square root function. What would the only difference be if this was y equals the square root of x and not the log base 2 of x? What would the only difference in the domain be? Ooh, I get asked a tough question here. With this one, the domain includes 0. It would be bracket 0 to infinity. So there are some similarities there with that one. But A lot of students never really grasp the concept of the domain of a logarithm. Why can't it be negative? Because you can't take a base and raise it to any power and result in a negative number. It just doesn't work.
What if the base is a negative?
Well, even if it's a negative, a negative times a negative is a positive.
Base.
Well, it depends on how many. On what power
If
it
you
is.
remember our discussion from last time, the base of an exponential is never negative. It's always positive. Therefore, the base of our logarithms are never negative. They have to be positive. Why? And maybe I should have gone into that last time. This is just kind of a side note. Why is the base of an exponential never going to be negative? Why would this not be considered an exponential function? Have you ever thought about that? Because this looks like an exponential function, right? The variable is an exponent. It's not an exponential function. Why not? If we made a table of values for this, you would see something very strange. If x equals 1, what do we get? Negative 2. But if x equals
Positive and negative make
if x equals 2, what do we get? Positive 4. Uh-oh. If x equals 3, what do we get? Negative 8. If x equals 4, we get 16. Do you see how the graph is jumping below the x-axis, above the x-axis, below and above?
Graph that, but just be like,
Yeah. So the base of an exponential is never negative. The base of a logarithm is never negative. Anyway, let's move on. Let's use some of these properties. Example 2. Evaluate. What was it, Jostens? Is that what it was? Oh. Lovely how they schedule that during class time. If I ask you to evaluate the log base 3 of 27, evaluate means tell me what it equals. The intent is that you use one of these 4 properties that we talked about here. Now, here's what's supposed to happen. The more you do with these, most of you, I would imagine, can start doing these in your head in like 2 seconds. 27 is a power of 3. So you would need to rewrite 27 as 3 to some power. What power of 3 is it? So you would want to rewrite this as the log base 3 of 3 to the third. Why would you want to rewrite it that way? Now we can use property 3. If you take the logarithm of a base of an exponential that has that same base, they cross out. Log base 3 cancels with that base of 3. What are you left with? So the answer is 3. The log base 3 of 27 is equal to 3.
So what happens when it's not?
The ones on your homework will be. If it's not, you'd have to use a calculator. We don't use calculators. Is there a way to check your answer?
Yes.
Just No, without a calculator. Just rewrite this. If you rewrote this in exponential form, what would it look like? 3 to the third does indeed equal 27, so it checks out. And what about this one? Part B. Log base, log base 2 of 64. What does that equal? What you're going to try to do is rewrite 64 as 2 raised to some power. Now, it's not a real common knowledge, but I think you can arrive at it. 2 times 2 times 2 times 2 times. How many 2's do you have to have in order to get 64? 6. So you want to rewrite this as log base 2 of 2 to the power of 6. Now that you have matching bases, log base 2 matches with that base of 2. So the answer is 6. These are some of the easy ones. You ready for some challenging ones? Did you guys have your Wheaties this morning? Well, that's a shame. All right, then. You asked for it, just remember.
No, we didn't.
Yes, you did.
No, we didn't.
Lying.
You're assuming. And you know what assuming does.
Log base. What? I mean, what?
I said you're assuming, and you know what assuming does.
No, I don't.
I don't want to say it so much.
Seniors excused to the auditorium at this
they got the seniors going.
Bye, guys.
Next thing you know, they're sophomores, and then the teachers.
Finish class.
You know that they said the teachers can actually still get their class rates.
All right.
Yeah. You're just going to go toss them out the gate.
I'm here.
The date, like 1848.
Yeah, when you're in high school. Yeah.
All right then. Juniors, you're interrupting us. Sit down and shut up.
Class readings are important.
Be like the good examples of our sophomores. They're intently listening.
I have a question. Can you have an exponent in the base of a log?
Wait, say that again.
Can you have an exponent in the base of a log?
Oh, I see these spots.
Suppose you could, but then you would just evaluate it and change it to an actual number.
Okay, so to simplify this one, would you put an exponent in the base, or would you do it?
The way that you do these, again, that's actually a good question. That's some good thinking there. The way that you do these, so you listening? You don't ever want to mess with the base of a logarithm. Okay? You have to mess with this 8. Now, the problem, the reason this is considered to be more difficult, it really isn't more difficult, but the reason it's perceived to be more difficult, usually the base is smaller than what's inside the logarithm, right? But this time the base is larger than what's inside the logarithm. It's different, yes. More difficult, no.
You just need to make the exponent.
Close. Not a negative exponent. The log base 64. How can we change 8 into 64 to some power? And I think James or somebody back there. James, what were you saying? You're saying a power of 1/2? Why a power? You are right, by the way. You are right. Why a power of 1/2? Where'd that come from? Square roots. The power of 1/2 is the same as the square. What's the square root of 64? 8. Now that we have matching bases, those are gone. So the answer to this question is 1/2. Now, that's a great way to do it if you're familiar with rational exponents and square roots. A lot of students are, and that's great. Some students really do have a problem with this. So let me show you an alternative. You ready for this? If you don't know what something equals, can't you just let it equal x? Right? Now, rewrite this in exponential form. This is going to be 64 to the power of x is equal to 8. Correct? You with me so far? Now, sometimes I lose students with this next step, but try to follow along here. Instead of 64, I'm going to write 8 squared to the power of x is equal to 8. Did I lose anybody there? Isn't 64 the same as 8 squared? Now what happens when you have a power that's being raised to another power? You multiply them. So now this is 8 to the 2x is equal to 8. You see what I'm doing here? If we now have matching bases here and here, the equal sign means that these two expressions are exactly the same. Well, if the bases are the same, then aren't the exponents also the same? So now just solve the equation in the exponents. If 2x is equal to 1, what does x have to equal? X has to equal 1/2. Therefore, the answer to this is 1/2. Yes, maybe it's a little longer way of doing it, but some students really struggle with rational exponents and all that other stuff. This is.
Could you do it the way could you put an exponent into the base? Because you know that 64 to the 1/2 is 8. So could you just do log base 64 to the 1/2 with 8?
I'm not sure I understand what you're asking. Say that one more time. Let me try to listen.
So could you put an exponent into the base of a log, like his log base 64 to the 1/2 of 8? Does that make sense?
Yeah, it's a coincidence that it happened to work on that one. You don't ever change the base of these logarithms. You always mess with what's inside the logarithm. How can we make this more challenging? You guys are breezing right through this. Oh, here we go. I got one. You ready for this?
And the last page.
Ooh, this is going to be a good one. I'm going to stump you for sure.
It's going to be really simple, huh?
Well, maybe for some of you.
for us to change
Let's do the log.
on the block.
It's just one log base 1.
Oh man. Here we go. I'm sorry to have to do this to you.
Easy. So easy.
Holy moly. Anybody got it?
Wait, give me 2 seconds.
Log base 9 of the square root of 3. Not too hard. We're just going to give up, right?
No, don't do it. I got it.
No, you guys aren't like that.
Yeah. I do. I have it. It's right here.
One of the, you guys have heard of this new common math core that started. Have you guys heard of this? Like secondary math 2, secondary math 1. You guys are aware that geometry's gone, algebra 2's gone. You guys are
Not until
aware?
we're done, right?
Not until next year. One of the initiatives in the Common Core is to try to further some characteristics, not just mathematical learning, but mathematical characteristics. One of those is perseverance. You guys know what perseverance is?
Keep going.
Keep going. Okay. One of the things that we're supposed to try to foster in our students is the ability to persevere. When a problem gets tough, not all students, but some students have a tendency to do what? Pencil down, I'm done, I can't do it. Yeah, that's not persevering. So, when something is difficult, try something. Try something else if the first time doesn't work. Does anybody think they've gotten somewhere? James, do you think you've gotten somewhere?
I got it.
Yeah.
You think you've gotten somewhere?
I think it's the 1/4.
What was your answer, James? A fourth?
1/4.
You got 1/4? Anybody brave enough to explain what they did?
Sure.
Did you get 1/4, Trent?
Yeah.
You want to explain how you...
Well,
Okay, listen.
so I wanted to get the square root of 9, so I put it to the 4th power. So it would be 3, the square root of 3 is the 4th power is 9. So then, and then 9 and around 9 is 1/4.
Yeah, that'll work. Did you guys do it the same, similar type of way, or?
I just kind of did it in my head because I know that the square root of 3 times the square root of 3 is 3. So back to the 4th. So the square root of 3 to the 4th power would be like 3 times 3, which is 9.
Okay. Here's a little suggestion, you guys. Pay attention to this. You listening? Logarithms and radical signs do not mix well. They really don't. Logarithms and radical signs don't play nicely together. It's like U of U fans and BYU fans. They hate each other. Okay? There's no hope for them. What I would always suggest, is you rewrite these radicals into their rational exponent counterparts. So I would write this as the log base 9 of 3 to the 1/2. I would always rewrite radicals as rational exponents. Always. Okay? Now the problem here is the 3. The 3 doesn't match the base of 9. What we've got to change is 3. But you can't just make changes to something. You've got to make sure that you make changes and you end up with an equivalent statement. For example, I could change 3 into 9 to the 1/2. Why can I make that change? Yeah, because 9 to the 1/2 is equal to 3. There are some changes you can make, some that you can't make. You can't make changes that's going to change the numerical value of your statement. Did I change the numerical value of my statement? No. Okay? Now that you have a power being raised to a power, you multiply those powers. So now you have log base 9 of 9 to the 1/4. Log base 9's cancel, so the answer is 1/4. All right, that was semi-challenging. Here's another one. I'm just trying to get you prepared for every situation that you might see on your homework. Log base 2.
So we already see this.
Yeah. Oh, this is a mean one. Oh, this is a mean one. Sorry. Log base 2 of 1/8. Let me, if for those, it sounds like some of you have got it. For those that aren't quite there, consider this. Whatever answer you get is going to be an exponent of 2. So first of all, what kind of an exponent is going to produce a fraction? So your answer has to be negative. That's your first hint. Okay? What kind of a negative exponent is going to change 2 into 1/8? Negative
3.
Negative 3. The answer is negative 3. All right, let's move on. Graphing. Graphing logarithmic functions. It's kind of similar to what we did last time. Do you remember last time exponential functions had a horizontal asymptote? Remember that? Well, logarithms are the inverse of exponentials. So instead of having a horizontal asymptote, logarithms have vertical asymptotes. Now, for those that came in late, because you're at the wonderful Jocelyn's thing, logarithms have a restricted domain. You can't let x equal anything you want. Logarithms have a domain from 0 to infinity. If there are restrictions in the domain, think back to the last section of the test we just took. Okay? This problem right here, y equals x plus 2 over x minus 5, if you were to graph that, wouldn't there be a domain restriction because of the denominator?
Yeah.
Well, what happened when you had a domain restriction on this graph? Vertical asymptote. Okay? Logarithms have domain restrictions, so they also have vertical asymptote. So let's consider example 3. Graph. We're going to start with y equals log base 2 of x. You're going to do these in the same order that you did your last examples for graphing exponentials. When you were graphing exponentials, what was the first thing you did? You put in the horizontal asymptote, right? So the first thing you're going to do here is put in the vertical asymptote. Okay? Where was that boundary of domain? The domain could be anything except where. Where did it end? 0. So on this graph, let's start. So draw a blank graph and put a vertical asymptote going through 0, going through the y-axis basically. Now, with rational functions, if you remember back from the last section of chapter 3, you could have the graph on either side of the vertical asymptote with rational functions. But with logarithm functions, think carefully before you yell out an answer. On logarithmic functions, what side of the asymptote is the graph going to be?
Left.
You gotta think, guys.
Left.
What's the domain of the logarithm?
That's right.
From 0 to positive infinity, right? From 0 to positive infinity. So what side of the asymptote is the graph going to be on? The right side. Okay? So the graph is going to be on the right side. Do we know where the points are yet? If you don't know where points are, what can you do? Plot points. Plot points. We're going to plot some points. Put the pencil down and give up. If you do that, I'll jam the pencil back into your face.
Yeah. Fun.
And then you'll never give up again. And you'll never see me again either. I'll be in jail.
Frankly, you won't be here to see it.
So let's just do this. -2, -1, 0, 1, 2. Those are the 5 points that every student likes to use, right? We can use all of those, right? We can't use the negatives. You cannot use. I was just seeing who was paying attention. You can't use negative numbers in logarithms, you guys. Doesn't fit the domain. Could we even use 0? Would 0 even work?
No.
No. So forget about it.
Find the nearest point or whatever to 0?
No.
Like
If you wanted to use a calculator, you could. Like 0, 0, 0, 1. What about the log base 2 of 1? If you plug a 1 in for x, ooh, this is one of our properties. If you plug a 1 into any logarithm, you get a 0. So 1 comma 0 is a point on the graph. Yay! We found one. Now let's let x equal 2. This is another one of your properties. What's the log base 2 of 2? 1. So 2 comma 1 is on the graph. Ooh, this is fun. We're just going to let x equal 3 just for the fun of it. Uh-oh. Problem here. What's the log base 2 of 3? A decimal. 3 is not a wise choice. Even though it is in the domain and it's a valid number to use, not a wise choice because we have to do this by hand. What's the next number in line that's a wise choice? 4. Why 4? It's a power of 2. You want to choose powers of 2. What's the log base 2 of 4? 2 cubed is 8, yeah. So if x is 4, then y is 2.
Look at this. It looks like a square root.
Now, if you just try to connect the points that we have, yeah, it looks like a square root, but I'm telling you, this is not all of it. We're forgetting a big part of it.
We're forgetting the side underneath the negative line.
What happens when a graph approaches a vertical asymptote? It either curves down or curves up.
We have to do like halves. And
You would, I mean, technically you would. I'm not going to ask you to do that by hand.
now we'll just curve down.
So when
Yeah. No, if it curved back this way, it wouldn't be a function. It wouldn't pass a vertical line test. Good question, though. How many points did we use? 3. That's all you need. 3 points. Okay. You graph the vertical asymptote and then just choose 3 points. Okay? Now, ooh, again, think carefully. Please think carefully before answering. Is the vertical asymptote always going to be a 0?
Yes.
Careful, guys.
Now, if you're saying the answer is no, I may ask you, well, give me a situation where it would not be a 0.
So yes.
I'm not saying that it couldn't be, or I'm not saying one way or the other, but if you're saying, no, definitely not, the vertical asymptote will not always be at 0.
I have a feeling there's a secret where you could make it not 0.
A secret?
Is it when you put a number in front of the log?
Okay, we're getting on the right track.
That's
When
right.
you
You can't
add
have
something to the end of the log?
We're getting on a closer track.
When you...
If the graph moves,
If you divide it.
okay, if the graph moves up or down, is that going to change the vertical asymptote? If the graph moves left or right, is that going to change the vertical asymptote? So where would a transformation have to be inside the parenthesis? Exactly. Okay, I don't want you to change anything in this example, but what if I did this, x minus 1?
Then it would move to the right one. Is that correct?
To the right.
To the right. It would move to the right. Inside the function is opposite. So if this were the case, where would your vertical asymptote be?
1.
At 1. But then other than that, you still choose 3 points, you graph it. Okay? So let's do one more quick example, then we are running out of time. We've got to move on. Let's do part B. I want you to graph y equals the log base 3 of x plus 1. Log base 3 of x plus 1. Where is the vertical asymptote now? It's to negative 1 because the graph moved to the left 1 unit. Now, didn't we just say that you couldn't put negatives inside of logarithms? But this graph is going to cross through the y-axis, and you are going to have some values of x that are negative. How's that work? Because you had the 1 added to it. Because you're not going to have any numbers that go less than negative 1. You're going to have negative numbers that are between 0 and negative 1. So if you take something like negative 1/2 and add 1, then it becomes positive. So you're good. So we need some points. We need 3 points to be precise. Now, we know that x cannot be negative 1. Because negative 1 plus 1 would be 0. You can't take the logarithm of 0. So negative 1's out of the picture. What about 0? If x is 0, is this even going to work?
Yes.
What's 0 plus 1?
1.
And the log of any base. It doesn't matter what the base is. Anytime there's a 1 inside of a logarithm, the answer is 0.
So 0, 0 is a point.
0, 0 is a point on the graph. And the next one, yeah, exactly. You want your x column, or not your x column necessarily, you want the whole expression inside the parenthesis to be a power of 3. Isn't 3 a power of 3? 3 is a power of 3, right? But if you let x equal 3, then you have to add 1 to it and it becomes 4. 4 is not a power of 3. So you don't want to let x equal 3, you want x to equal 2. Because when you add 1 to it, it becomes a power of 3. You follow? So if x is equal to 2, 2 plus 1 is 3. Log base 3 of 3 is equal to 1. So 2 comma 1 is on the graph. And finally, we need one more power of 3.
8.
9 is a power of 3, so we're going to let x equal 8. 8 plus 1 is 9. Log base 3 of 9 is 2. So 8 comma 2, 1, 2, 3, 4, 5, 6, 7, 8. 8 comma 2 is a point on the graph. I have seen many students mistakenly think, okay, the graph looks like this. Yeah, that's part of it. What are they missing? The graph has to approach that vertical asymptote, and then it tends down towards negative infinity. They're what?
I can see that they're inversely correct.
They are. They really are.
That's a great way, like you could almost, instead of doing like log functions, you could always try and do an exponential function.
I've actually seen teachers teach it that way, and it's not a bad way to do it. Did everybody understand what he was saying? Rather than graphing an equation in logarithmic form, what if we rewrote this into 3 to the y equals x plus 1? Aren't these the same thing?
Yes, but the other one makes more sense.
So you could graph it in this. You could graph it in this way. Now, if you graphed it in this method, I would actually recommend that you choose your y values instead of choosing your x values. For example, if you let y equal 0, then what's 3 to the 0? 1. And then if you subtracted 1, what does x equal? 0. So now you get 0, 0. And now if you let y equal 1, 3 to the first power is? What's 3 to the first power? So now you'd have 3 equals x plus 1. If you subtracted 1, you would get x is equal to 2. So you end up with the same points, right? So I've seen a lot of teachers teach it that way. It's not a bad way. Can we move on from graphing? We feel good on graphing? Okay, last objective. I think it's the last objective. Let me check. Yeah, we're on the last one. Cool. The last one is what's called the common logarithm and the natural.
Oh, this is for the element.
Yeah, exactly. The common logarithm and the well, it loves you. The natural logarithm. Let's start with the common log. I mean, these are really easy. The common log is just a logarithm with a base of 10. The reason it's called the common logarithm, our number system, just a lot of students don't ever understand this discussion, but our number system is a base 10 number system. Does that make sense to anybody? A base 10. We use decimals, right? What does the word deci mean? 10. Our number system is a base of 10 number system. Like this number, for example, 142. Okay. If we broke this up, wouldn't that be the same thing? Okay. Now if we broke this down even further, isn't that the same thing? Have you guys ever seen something like this? This should be an elementary school discussion that you have in elementary school, but
The power of something.
maybe not in elementary, I don't know. But do you understand why this is called a base 10 number system? Okay? So a common logarithm is just a log base 10. You guys, you'll never ever see it written as log base 10. You will always see it written like this. LOG with no base. If there's no base on the logarithm, what's the base of the logarithm? 10. It's a common logarithm. Okay? Where you would see this come into play is this example here. Rewrite this. Quick, we're running out of time. Rewrite log of 1000 is equal to 3. Rewrite that into exponential form. Log of 1000 is equal to 3. Well, you notice there's no base in that logarithm. That's because it's a base of 10. So what would this look like in exponential form? 10 to the third equals 1000. That's how you might see this used. Later on in this unit, I think it's lesson 4.6, we're going to look at the pH scale and the logarithmic scale, or the Richter scale. Those all include logarithms of base 10. Natural log. That's a logarithm with a base of e, because e is the natural number. So the natural logarithm is a logarithm with a base of e. You will also never ever see it written this way, ever. You will always see it written this way, ln. Natural log. It's log natural. Logarithmus naturalis. It's Latin. And Latin, like Spanish, the adjective comes after the noun, right?
Is that really?
Yeah.
I thought you were just making stuff up.
Sometimes I do make stuff up, but not this.
Sometimes.
All that can sound like
Yeah. Well, it's a Latin. Logarithm is a Latin term, so this is a Latin. Anyway, you'll see it written as the natural log ln. So where you would see this is, if I gave you this expression, rewrite e to the x is equal to 9. What would that look like in exponential form, or in logarithmic form rather? Logarithmic form. This would look like the natural log of 9 is equal to x. And again, some students are really good at remembering what goes where and this drops down. Other students are not. I would recommend that you not try to memorize what goes where. Try to understand what's happening. What gets rid of a base of e? A natural log. So you have to do a natural log on both sides. Those would then cancel out. What are you left with? X equals natural log of 9. Okay? And, ladies and gentlemen, I'm just double checking. We is finished.
Yes.